Welcome back to our course, Networks and Distributed Systems, based on the textbook Computer Networking, a Top-Down Approach by Jim Caros and Keith Ross. We're in Module 5, which is covering the link layer of the TCP/IP model. In our last lesson, we had just concluded discussing Ethernet and switches. So why don't we pick up where we left off? Earlier, we noted that modern institutional LANs are often configured hierarchically, with each work group or department having its own switched LAN connected to the switched LANs of other groups via a switch hierarchy. You can see that demonstrated in the image on the screen. There are three drawbacks to the design you see depicted. There can be a lack of traffic isolation. Although the hierarchy localizes group traffic to within a single switch, broadcast traffic, such as frames carrying the ARP messages or DHCP messages or frames whose destination have yet to be learned by a self-learning switch, must still traverse the entire institutional network. Limiting the scope of such broadcast traffic would improve LAN performance. It also may be preferable to limit LAN broadcast traffic for security and privacy reasons. For example, if one group contains the company's executive management team and another group contains disgruntled employees running Wireshark packet sniffers, the network manager is sure to want to prevent the executive's traffic from ever reaching those employee hosts. This type of isolation could be provided by replacing the center switch in this image with a router. However, we shall also see that this isolation can be achieved via a switched solution, a layer 2 solution, a link layer solution. Another drawback to the arrangement in this image is the inefficient use of switches. If instead of 3 groups, the institution had 10 groups, then 10 first-level switches would be needed. If each group were small, say less than 10 people, then a single 96-port switch, for example, would probably be large enough to accommodate everyone. But this single switch would not provide traffic isolation that we might want between the 3 departments. There's also an issue of managing users. If an employee moves between groups, the physical cabling must be changed to connect the employee to a different switch in Figure 515. Employees belonging to 2 groups make the problem even harder. Fortunately, each of these difficulties can be handled by a switch that supports Virtual Local Area Networks, VLANs. As the name suggests, a switch that supports VLANs allows multiple Virtual Local Area Networks to be defined over a single Physical Local Area Network. Hosts within a VLAN communicate with each other as if they and no other host were connected to the switch, even though in fact they are actually sharing the same physical switch with another VLAN. In a port-based VLAN, the switch's ports, or interfaces if you prefer, are divided into groups by the network manager. Each group constitutes a VLAN, with the ports in each VLAN forming a broadcast domain. That is, a broadcast traffic from one port can only reach other ports in the group. Figure 525 shows a single switch with 16 ports. Ports 2 to 8 belong to the electrical engineering VLAN, while ports 9 to 15 belong to the computer science VLAN. Ports 1 and 16 are unassigned. This VLAN solves all the difficulties noted above. Electrical engineering and computer science VLAN frames are isolated from each other. Two of the switches in Figure 5.15 have been replaced by a single switch, and if the user at switch port 16 joins the computer science department, the network operator simply reconfigures the VLAN software so that port 16 is now associated with the computer science VLAN. If we had used a 24 or a 48 port switch, we could just as easily have added the third VLAN for the computer engineering VLAN. One can easily imagine how the VLAN switch is configured and operates. The network manager, using switch management software, declares a port to belong to a given VLAN, with undeclared ports belonging to the default VLAN. A table of port to VLAN mappings is maintained within the switch, and switch hardware only delivers frames between ports belonging to the same VLAN. But by completely isolating the two VLANs, we've introduced a new problem. How can traffic from the electrical engineering department be sent to the computer science department? One way to handle this would be to connect a VLAN switch port, for example port 1 in Figure 525, to an external router and configure that port to belong to both the electrical engineering and the computer science VLANs. In this case, even though the electrical engineering and computer science departments share the same physical switch, the logical configuration would look as if electrical engineering and computer science departments had separate switches connected via a router. An IP datagram going from the electrical engineering to the computer science department would first cross the electrical engineering VLAN to reach the router, and then be forwarded by the router back over the computer science VLAN to reach the computer science host. Fortunately, switch vendors make such configurations easy for network managers by simply building a device that contains both VLAN switch and router, so a separate external router is not needed. Considering the Figure 5.15 we were just looking at a few slides ago, let's suppose that rather than having a separate computer engineering department, some of the electrical engineering and computer science faculty are housed in a separate building where they need network access, and they should be part of their department's VLAN. Figure 5.26 shows a second 8-port switch, where the switch ports have been defined as belonging to the electrical engineering or the computer science VLAN as needed. But how would these two switches be interconnected? One approach to interconnecting VLAN switches is known as VLAN trunking. In the VLAN trunking approach, as shown in Figure 5.26, a special port on each switch, port 16 on the left switch and port 1 on the right switch, is configured as a trunk port to interconnect the two VLAN switches. The trunk port belongs to all VLANs, and frames sent to any VLAN are forwarded over the trunk link to the other switch. But this raises yet another question. How does a switch know that a frame arriving on a trunk port belongs to a particular VLAN? The IEEE has defined an extended Ethernet frame format 802.1q for frames crossing a VLAN trunk. The 802.1q frame consists of the standard Ethernet frame with a 4-byte VLAN tag added into the header that carries the identity of the VLAN to which the frame belongs. The VLAN tag is added into a frame by the switch at the sending side of the VLAN trunk, parsed and removed by the switch at the receiving side of the trunk. The VLAN tag itself consists of a 2-byte tag protocol identifier field with a hexadecimal value of 81-00, a 2-byte tag control information field with a 12-bit VLAN identifier, and a 3-bit priority field that is similar in intent to the IP datagram TOS field. Now, in this discussion, we've only touched on VLANs and have focused on port-based VLANs. We should also mention that VLANs can be defined in other ways. In MAC-based VLAN, the network manager specifies a set of MAC addresses that belong to each VLAN. Whenever a device attaches to a port, the port is connected to the appropriate VLAN based on the MAC address of the device. VLANs can also be defined based on network layer protocols, such as IPv4, IPv6, or AppleTalk, and other criteria. So there we've covered a brief introduction to VLANs. And that takes care of as much as I want to cover in this particular course on the link layer. Now we're going to move on to another module, Module 6, but you go ahead and review your notes and update your study guide, and when you're ready, come on back and we will start that new module.